All right, a chapter that I really like talking about. It's chapter 7, because the title is Power, and I like power. I like power. Remember, what was it, Tim the Tool Man? Remember power? You could never have enough power. You know, the gas-powered blender. I think it's a great idea. You know, if you've ever mixed any frozen concoctions, having a little bit extra power there to chop that ice up and, you know, get just the perfect consistency is not a bad thing. So I've never driven a car. I've never driven a car that's had too much power. I think, actually no, and I did have the opportunity. I went through Richard Petty's driving school 2 years in a row. This is probably about 10 years ago. And I thought these cars would have governors on them. You know, you go through and they're going to turn some goofball like me loose in a, you know, in a Winston Cup car at the time. No governors. That car had a lot of power. Okay, put in the right hand. It scared. I got to drive Las Vegas Motor Speedway, and I turned the hot. I'll tell you the whole story sometime, but I got the fastest times of the day. I was at the top of the reader board, Joe Grenick, you know, it was pretty freaking cool. So I was thinking about quitting my day job and becoming a NASCAR driver. So luckily I have good friends that, you know, woke me up to reality. But the power was fabulous. So I think, though, as much as I love aviation and aerospace, you know, I see the Blue Angels in town, I look at those F-18s, and knowing my own piloting skills, and I think I'm a pretty good pilot, but knowing my own pilot skills, I'd probably last 5 or 6 seconds in one of those things before there'd be a fireball going down the runway. A little bit too much power for me. Power in electronics is in electrical is very, very important because it's the metric that we use to determine output. It's the metric that we use to determine efficiency. It's the metric that we use to show us how much energy we're converting into work. So this is a really big chapter. If you fully understand the implications of power, you're going to be a better technician. You truly are, because looking at inconsistencies in power output is going to start to paint a story, tell you a story, and paint you a picture of what's taking place with a system. So with that being said, let's jump and immerse ourselves into Chapter 7, Power. After completing this chapter, we're going to be able to define power as it relates to electric circuits, state the relationship of current and voltage, solve for power consumption in an electrical circuit, determine the total power consumption in a series, parallel, and a series parallel circuit. Now, power relates to the rate at which work is being done. Relates to the rate at which work is being done. Work is done when a force causes motion. I'm sure my kids, I got 3 kids, 3 boys, you know, they're all like grown. The youngest is going to graduate the UW here in June. Business finance, he's going to make a bunch of money and then like hire me to like hang out with him. He's going to do really well. But my kids probably all think I'm a jerk because I know stuff like this. You know, we'd have, you know, family cleanup day around the yard. And I'm out in the front yard digging ditches and doing whatever, and the kids are in the backyard supposed to be raking leaves. And I come around the corner, and they're standing there leaning on the rake. What are you guys doing? We're working. No, you're not, because work is done when a force causes motion, right? So by simply standing there, bracing yourself against the rake, you're definitely not working. To get back to work. So obviously me knowing this stuff, they think I'm a jerk. So work is done when a force causes motion. Now check this out. Force, voltage. Current, motion. Voltage creates current, causing electrons to move in a circuit. So if you've got a voltage and you've got current, you're doing work. May not be the work you want to get done, but you're doing work. Because a force causes motion. Voltage causes current. And we know voltage is pressure, current is movement. It's got to be power. Make sense? Now, electric power rate is the instantaneous rate at which work is done. Instantaneous. That means take a snapshot right now. How much work is being done right now? What's the pressure? What's the current? Right? now, instantaneous value. Make sense? Now, that's not how the power company, it's actually odd the power company is called the power company. Let's go back to that. Power relates to the rate at which work is being done. Work is done when a force causes motion. How many of you here pay money on a monthly basis to the power company? The power company. Why are they called the power company? All they're really providing us with is voltage. You know who the power company is? It's you. It's to take money out of our wallets, exactly. Who's the power company? You're actually the power company. You're providing the current path, if you will, for the current to flow. They're just providing you with the voltage. They should be called the voltage company. Okay? I mean, realistically, that's all they're doing. When you pay for electrical service to your home, all they're providing you with is a voltage, a electrical pressure at your box. It's up to you to hit the breakers, turn the circuits on, turn your lamps on, turn your appliances on, turn your loads on. That gives current a path to flow. Now you're consuming power. Power company. I always, I take this stuff too literal, which is one of the reasons that I'm here and you're there, okay? But it just doesn't make sense, does it? It really doesn't. Now the power company, the voltage company, charges you in watts. Actually, the power company charges you in what are called kilowatt hours. Kilowatt hours. I'll talk about more of that in a second. Measured in watts, wattage is greater when work is done in a short period of time than when the same amount of work is done in a longer period of time. Wattage is greater when work is done in a short period of time than when the same amount of work is done in a longer period of time. All right? A mild example of this, it's an area of, I enjoy motorsports in general. I enjoy mechanical things. No offense to any of you here that are into any of the fine arts. But if I had a chance on a Sunday afternoon of going to the opera, which I've attended, the opera, a symphony orchestra, musicals, plays. I'm not a big musical guy, no offense, but it's not how I roll. Or going down a Boeing field and standing at the edge of the fence and watching the heavy metal take off. Okay, I'd probably be down a Boeing field. It's just how I roll. So I've always been a big advocate of motorsports. One area of motorsports that I never was really that intrigued with, I respect it, but I'm not that intrigued with pursuing it, is drag racing. But I respect it immensely. Drag racing is about getting as much power out of the engine and coupling it to the wheels and getting the car down the track, quarter-mile track, as quickly as you possibly can. And if any of you have ever watched drag racing, some of the rockets, strap yourself in, go, pow, wow, quarter mile, a matter of seconds, and they're down that quarter-mile track. I've always been, I've enjoyed NASCAR racing, and Formula One for me is it. Because they not only go down the track that fast, but they turn around and come back, and they make some turns in between. So that's really amazing technology. But follow what I'm saying? Drag racing takes all of that power, couples it to the wheels, the tires, traction, and accelerates, okay? So they're consuming a huge amount of power and converting it into energy to get down the track.
Would that be the same concept if you had a car that did 45 miles in 1 hour versus a car that did 80 miles in 1 hour? You would be consuming more power.
Absolutely.
80 miles an hour, but you can get there faster.
Absolutely. Yep. And to get that work done in a shorter period of time, it's going to take you more power. So that's one of the reasons that, with gas prices going up, getting off that pedal does make a difference. Does make a difference. The epitome for me, and it's a toss-up. It's a toss-up. NASA was involved in both of them, right? Space shuttle. Space shuttle, or kicking it old school NASA, the Saturn V rockets. Saturn V rockets, a little tiny capsule up on the top, big, huge freaking rocket, okay? Light it. The dude that lights it and then goes like 3 miles away and goes into a concrete bunker, okay? And then literally with the space shuttle, it's the same thing. They light it, and then they run 3 miles away, and thing goes off, right? 7 minutes later, they're in outer space. 7 minutes later, they're in outer space. NASA throws power at the problem to get the space shuttle into orbit, okay? So obviously we're talking about, if NASA could meter out that power, you could probably light several cities for a good deal of time. Instead, they say, how can we get that power and concentrate it in liquid fuels, solid rocket boosters, and then be able to concentrate that energy so we could get that space shuttle, which is freaking huge, it's a big thing, into outer space in 7 minutes. Not 8 minutes, not 9 minutes, but in 7 minutes. They're in orbit. Tremendous amount of power. Have any of you here ever seen a space shuttle launch? Okay, I had the opportunity back in the 80s. I actually saw the Challenger. Fortunately, not the time that it had its malfunction. I saw it before that. And actually, ironically, Dick Scobie, who's from Auburn, Washington, I saw a mission that he flew prior to the catastrophic accident that they had. But I was in Titusville, Florida. And you know, you're listening to the radio and you hear the countdown and everything, 3, 2, 1, and you know, I don't know how many miles away you are, like 10 miles, 12 miles. You know, you see it going up, and then all of a sudden, then the wall of sound hits you, and it's just a sound like I've never heard before. It's like, wow, that is freaking cool, you know. And next thing you know, it's gone, man. It's in orbit. They're in orbit, orbiting around the Earth. Tremendous amount of power. Okay, so it's the same thing with electronics. It's the same thing with electronics. The more power we throw at something, the more work we can do. So, you know, basically, you know, if you're attending a concert, you know, the Pink Floyd Orchestra is performing in an auditorium, they are going to have to throw a lot of voltage and current at the problem to create a lot of acoustic energy to satisfy the masses, because that's what we've all grown accustomed to, is loud music, right? Okay. Watt is the basic unit of power. That is not a question, it's a statement. Watt. Watt is the basic unit of power. It is literally equal to the voltage across a circuit multiplied by the current through the circuit. It represents the rate at which work is being done. And Watt is the guy that came up with it. And what he said, I think he gave this presentation down at the Kingdome back in the day. 45,000 people. Ohm gave his spiel. Right? Remember that? V is equal to I times R, right? That was Ohm's deal. Watt got up there, not to be outdone, and he said P is equal to I times V. And that's what he said. That's what he said. So, again, P, I, V. Triangle with a T in the center. Power is equal to voltage times current. If I ask you how much voltage is there, and you know how much power there is, right, in current, then you could calculate out the voltage. If I ask you how much current is there, if you know the power and the voltage, you could calculate out the current. And of course, power is current times voltage. That's all your variables. Simple math. And this is called Watt's law. Watt's law. So far, for those of you at home keeping track of what's going down, we've gone over Ohm's law, we've talked about Kirchhoff's law, and this is Watt's law. These are laws of physics. They allow us to calculate what's going to take place with 100% accuracy. Very, very useful tools. We're not teaching you this stuff because I got nothing better to do with my time. We're teaching you this stuff because this becomes very valuable for an electronics technician. It paints a picture, tells you what's going on. Literally tells you what's going on. Okay? A little known fact about yours truly. I used to work in radio. Okay? I worked on the air. I was an on-the-air personality for an AM radio station in Connecticut. And it was one of the things that got me interested in electronics, because I worked kind of hard and I didn't have a whole lot of job security. There was a guy at the station, the chief engineer. This guy, every year he'd have a new, he'd buy a Formula Firebird, trade in the old one, get a new Formula Firebird. And he always kind of had a girlfriend with him that was kind of had it going on, if you know what I mean. Okay? And he did very little. He came every week to the station, and he'd get all of the readings that all the on-the-air people took from the transmitter. We were able to take the readings from the transmitter remotely, but we had to log in these voltages and these currents. And then he would come. He'd come with a calculator, much like this, right? And he'd sit there and he'd perform these calculations all the way down, and then he'd sign the logs, take them, stick them in a folder, and then they'd be held by the station. What he was doing is that the station, commercial station, was licensed by the Federal Communications Commission to only broadcast so much power. And the proof of how much power was being transmitted was the voltage of the final transmitter tube, the current flowing to that transmitter tube. If you knew those two, you could calculate out the power. And then there was approved engineering design criteria for the antenna system, that the antenna system had certain number of losses. So you could prove to the FCC, you see, we were not broadcasting more power than we were allotted. We were not interfering with that station in Pennsylvania, okay? We couldn't have been, because we're only broadcasting out what you've allowed us to broadcast out. So as a technician, calculating this out through the current and voltage readings, that I think it was every 4 hours we had to take. Every 4 hours on the air personnel, and it was right there in the studio. It was an equipment rack, and you could go and just sequence through, you know, and take the voltage readings, the current readings, and log those in, and that became part of the permanent record. So it was kind of it was kind of funny. It really was inspirational for me seeing this guy as the chief engineer. He was a chief engineer, and he was assigned several radio stations in Connecticut on contract. Guy made really good money, you know, and I'm like, how do I get his job? Well, you need an FCC license, you know, basically the general radio operator's license to be able to maintain a commercial radio station like that. So anyway, I'm an examiner now for the FCC, and I give that exam, and I've never in my life owned a Formula Firebird. So I have had some girlfriends that kind of had it going on, if you know what I mean.
It sounded like a pretty easy job you had, though, huh?
Until it hits the fan. Until the station gets hit by lightning, okay? And then it's like, oh. And then you got the general manager, right, the program director, and all of that advertising dollars that were spent, right? You're losing that money because the station is off the air, and that's how stations pay the bills, is all the advertising. So when you're off the air, you're in a pickle. People will tune to another station or whatever. So it's kind of a big deal. Ironically, though, kind of behind the scenes story, like here, we had a woman in our program that completed this program, and I got her an internship. She interned for a period of time at KISW. And the engineer at the time over there, Brian, he hadn't had a vacation for 3 years. Because again, as a chief engineer, you just don't go on vacation. Yeah, I'm taking my vacation next week. You can't do that. Because if the station goes off the air, who's gonna, you know? So there was nobody that he could hand the station over to. Once she got in there and she built up some credibility, he actually went on vacation and gave her the keys, and it's kind of like, hey, you've got it, Cindy, you've got the station. She was a student here at Lake Washington Technical College, and she was the acting chief engineer for KISW. Also, because all these engineers and all the radio stations in Seattle, they're all in cahoots with each other, okay? So if the station goes off the air, you know, call Tony over at Cairo. He'll come over and help you out. You know, you've got all these engineers that will lend a hand, even though you're the competition on paper. If I need something, you'll help me out. If you need something, I'll help you out. And it kind of goes, it's a, you know, unwritten law, if you will, in radio to help everybody else out. So kind of exciting. So anyway, this power reading is very, very critical, so that you could tell the performance of your equipment. And it's something that, if any of you go into commercial broadcasting, you're going to be doing the exact same thing, taking those power readings. How much energy are we getting off the antenna? The only way of telling is how much voltage you got, how much current you got going. Same thing. You come from an audio car audio background, same thing. You got a 1,000-watt amplifier. It's a math problem, okay? 1,000 watts, you know what this is, okay? 12.6 volts DC. You know what this is? Well, this is going to tell you how much current it is. It's a math problem, you know. Now, it's 1,000-watt amplifiers. That's peak performance, and how often you're going to be cranking out that peak performance. But you've got to design everything backwards to make sure that if you crank it up all the way, you're not going to cause an electrical fire and subsequent meltdown. So you've got to design, and it all integrates. Really, it's a beautiful thing. Now, the electric company, the voltage company, they charge you for kilowatt hours. kilowatt hours. That's 1,000 watts, a kilowatt, right, per hour. So that's you consuming 1,000 watts over an hour, okay? I don't know if any of you go to the gymnasium periodically, the gym, workout. Some of the life cycles, stair steppers, these things, some of them have integrated in calories that you're consuming. Some of them have a screen that you could go to for watts, okay? So I often thought, I hate working out. I really do. It just is, I'm not afraid of hard work. Okay, if I got to dig a ditch in the backyard, I love doing it. You know, I'm all about hard work. But going to the gym and like, for an hour just doesn't make sense. At least hook the thing up to a generator. Let me charge my cell phone or something, and let me save a nickel or something. If that makes more sense to me. But anyway, some of these screens have watts, and if any of you have ever done that, how hard you have to work to generate a watt. I mean, it's amazing. So the electric company, the voltage company, is selling us 1,000 watts per hour. That's the unit of measure that they charge us. Okay? Does anybody know off the top of their head about what we're being charged here in the greater Seattle area per kilowatt hour? Bzz. Way too much. You're being ripped off, man. That's Greenwich Power and Light. It's about 8 cents. About 8 cents. Some of you, depending on your scale, 6.5 cents, 7 cents per kilowatt hour, which is the thing that I kind of struggle with. I go this year alone. Since January, I got invited to attend a green energy conference, Good Jobs, Green Jobs in Washington, D.C. And then I was invited to be a guest speaker in Milwaukee at the Green Summit. So some world-class speakers I get to be in the presence of. So I go to this like Green Summit in Milwaukee, and I get seriously jazzed. I'm going to go home and I'm going to do an energy audit. I'm going to see. And then I get home. It cost them 6.5 cents per kilowatt hour. How much effort do I have to put into really saving? How much am I going to save? It really doesn't make sense. I mean, it really doesn't. There needs to be consumer incentive for you to really hunker down and save, because electricity here in the Northwest is very, very inexpensive, and that's a good thing. I'm not complaining about it. And there are some things that you could do to save energy, but there's only so much that you could do, and we're really not paying that much for it. Even like with electric cars, I know my colleague did some of the math with purely electric cars that they're coming out with, and really it equates, for the price of gas at $4 a gallon, it comes out to being that it's about 99 miles per gallon that you would get equivalent to travel 99 miles than it would cost you for that fill up. And that's what it equates to when you're paying 6.5, 7 cents per kilowatt hour, which isn't bad. I wouldn't mind having a car that got 99 miles per gallon, 100 miles per gallon. But is it worth the investment of me scrapping my, my V8? I mean, because unless I'm driving a Tesla, which is out of my range, I don't think I like that V8. V8 Taurus, pour some fuel into the situation, a little bit of air, get out of the freeway, set the pace, not keep up with the flow of traffic, set the pace. And I have documentation from Washington State Patrol that will attest to that fact. Okay. Circuit analysis to determine the power dissipated by a component and voltage drop times current. So I'm talking about for a component now. Okay, this works for loads. This works for like an amplifier. If you got an electric load, an amplifier, a transmitter, you could do this. But this also works for individual components. So if you know how much current's going through the component and you know the voltage across the component, then you could figure out exactly how much energy that component is dissipating. Now, remember resistors? Remember resistors? Resistors are devices designed to possess the property of resistance. Resistance is that force which opposes the flow of electrons. The byproduct of resistance, when current encounters resistance, it generates heat. That's how we determine the power of that resistor, because all resistors are not created equal. There's 1/8 watt resistors, 1/4 watt resistors, 1/2 watt resistors, 1 watt resistors, 5 watt resistors. How much energy could they dissipate? And literally, it's the voltage across the component times the current going through the component that's going to give you that power that's being consumed by it. If a resistor, if you ask too much of a resistor, it will fry. It will fail if you exceed its rated capability. So all electronic components are really like that. If you know the voltage, you know the current. We're going to talk about some exceptions in the future. They're not resistive components, they're called reactive components. That'll come later this quarter. We'll talk about that. And these are components that don't consume energy in the form of heat. That's why they're called reactive, but something we'll talk about in the future. Hey, the neat thing with power dissipated in series or parallel is equal to the sum of the power dissipated by the individual components. Power is always additive. It doesn't matter if it's series or parallel or whatever. Power is always additive. If I've got a 400 horsepower engine on my airplane and I remove it and get another 400 horsepower engine and mount each engine on each wing, now 400 times 2 is I'm up to 800 horsepower worth of power. As where before in a single engine aircraft, I was only up to 400 horsepower. Okay? It's kind of funny. I know a little bit about airplanes, but the odd thing about airplanes is when you do that, instead of the airplane costing twice as much, it ends up usually costing you about 3 times as much. So for a twin engine airplane, you're going to pay through the nose. You know, much higher performance, a lot more going on with it, a lot more structural that they have to do. But power is always additive. That's why the space shuttle, right? Solid rocket boosters on the space shuttle, right? They have 2. You know how much power that is? Twice as much as 1. Okay? That's why they put 2 of them on. And actually, from what I understand, I think the space shuttle can, I don't know if it can get a shallow orbit, if it's just on 1 solid rocket booster or not. But those things are literally like Roman candles. Once they light them, they're going for a ride. There's no shutting them down. Oh, we changed our mind. Let's back it back to the pad. No, you're going for a ride. Power. So power is always additive. Always additive. This is the thing like with your home. Forget about what I said. Energy conservation, a bunch of hocus pocus in your home. Every device that is on in your home right now that has a voltage across it and current flowing through it is consuming power. Okay, there's a lot of phantom loads in your home. Stuff that's plugged in but it ain't turned on, but it's still consuming power. Why? You got voltage across it, it's got current flowing. You're plugging the screen. How many have a nice flat screen TV at home, right? How many have it, is it turned on right now? You leave it on 24/7 or is it turned off? Still consuming power. Still consuming power. So that way when you go home and hit that remote, that screen comes right up. If not, there'd have to be a period of time with some electronics for it to warm up, come up. Everybody wants instant gratification with systems. Especially some of the old tube systems, right? Those really consumed a lot. You had to wait for the tubes to heat up and everything. But most electronics are really in a standby mode. Your battery charger right now, your cell phone charger at home, if it's plugged in the wall and it's not plugged into your cell phone, it's still consuming some energy because it's got current flowing through a coil there. When you plug in your phone, it consumes more current, right? So a lot of these, again, are phantom loads that exist in your home. You're consuming energy. Real small amount, but it all adds up. It all adds up, you know. Actually, one of the things I can give you a sales pitch for tomorrow's meeting, where I can watch a documentary called Power Surge that was just done on public television last week. It came out. They talk a lot about that. You know, it all adds up. It's all about power. You know.
About the lady that unplugged everything in her house for a month.
Oh, I didn't hear about her.
No. As soon as she was done using it, there was nothing that was plugged in.
Did she save money?
Yeah.
Really?
Decent amount, yeah.
Huh. I'm not going to do that. All my plugs are like behind the couch and crown. I'm not going to climb back there. It's all a power strip with an on-off switch.
Hit the main breaker.
You know, that's it. And in all honesty, that actually, I thought about that. You know, my wife and I travel a lot, and we go away, and really would make sense. Just shut off that main breaker of the house, you know. Leave for a month, come back, and then, you know, you go get your electric bill, and they still charge you the same. You know, they're just messing with you, man. They're just messing with you. You got to have your ducks in a row, man. You got to pay attention to that meter. So, Now, in electronics, the power dissipated in a circuit is often less than 1 watt. Electronics, microelectronics like you're studying here, typically the value is going to be less than a watt. Typical values will be the milliwatt. This is times 10 to the negative third, or 1,000th of a watt. And the microwatt. 1 million microwatts equals 1 watt. So we're talking a millionth of a watt. That's typically what's consumed in microelectronics. There's not going to be heat or energy being consumed. For some of you playing around with amateur radio, you want to get your amateur radio license and play around with some of that stuff. Some of them are higher power transmitters. You need to make sure you have the available current and voltage to signal out. Now, you're not going to be able to do that because, again, here behind the lie, power is equal to current times voltage. So if you're on a low voltage system, like a car or a boat or an airplane, and you want to start jacking this value up, that means you're going to have to start using a bigger cable, physically bigger cable, because you have more electrons that you're going to have to transport from the source to the load, and that's what you're measuring. Okay, so the math doesn't lie. Total power dissipated in a series or parallel circuit is equal to the sum of the power dissipated by the individual components. Meaning, power is additive. Power is additive. There's no such thing as negative power. There's nothing that's going to take, but this is putting power back in, perpetual motion machine. You get something like that going, give me a call. Okay, give me a call. I'll have my attorney contact your attorney, and I'll personally fly you to Bimini. And you could watch the sunset drinking out of a coconut with one of those screwy straws, an umbrella on the top of your drink. I'll take care of you. Okay? Now, all we do is consume voltage, current, we consume power. Nothing puts things back in. So it's not, I guess it'd be like me getting an airplane engine, mounting one, like going this way, and then the other engine going this way. And then you just sit there, you never go anywhere.
Wait, spin around in a circle.
One thing that way. Then they just lift off. It's a UFO. No, it's a doofus. it's a doofus. What's that guy doing? Does that make sense? All right, summary. Power is the rate at which energy is delivered to a circuit. Power is also the rate at which energy or heat is dissipated by the resistance in a circuit. This isn't that second bullet statement there isn't something we dig. It's something we got to deal with. We don't want our electronic equipment to get hot. It's one of my problems. I got a lot of electronics in my family room. Got my audio. I got surround sound. I got my plasma screen TV. I've got all this equipment. I got several computers. I got a computer that monitors the weather at my house. Why? Because I'm just into that kind of stuff. I got my other main computer. I've got all my network gear for router. I got a switch that powers the other internet connections in the house. I got all that stuff. In the summer, that room really gets freaking warm. Okay, in the winter, it's kind of cool. Warm, I mean. You know what I mean? You come in there, and I got all this electronic stuff that's keeping that warm, relatively in temperate. But, was it last year, 2 years ago, we had that heat wave? It was like, holy cow, man, I had to start shutting stuff down. I'm like, how important is it to shut this stuff down so I don't have a Wi-Fi system in the house? Not that generates that much heat, but everything else in there does generate the heat. We don't want that. We don't want that. It's something we have to live with. So a lot of times when equipment is densely packed, that thermal profile tells us what's going on. Former member of our advisory committee here at Lake Washington Technical College was the chief engineer for Channel 9 out of Seattle. And we went down there for a tour one day. Their transmitter's located up on Capitol Hill. And he was showing me the air inlet temperature and then the exhaust temperature, right? The air that they're sucking in to run through the transmitter to cool it. And by looking at that, this is the inlet air temperature, this is the exhaust. By looking at that difference, obviously if it's a warmer day, they go up like this, right? I mean, it is what it is. By him looking at that, okay, if this stays stationary and then this one goes up, it immediately tells him what? The transmitter's consuming more power. That means there's a problem. Because when it was brand spanking new, this is what it was. This is the inlet. The difference between the two is a critical number. Temperature. You raise the temperature, shows you something's not operating efficiently. plain and simple. One of the tricks, because I paid attention. I'm not that smart of a guy, but I did pay attention when I was in school, formal schooling like this. One of the things that I used to do is when I was in the Navy, we had very, very complex circuits. And there was this one board that had memory chips on it. And it used to fail. And running the diagnostics to determine which chip it was just very, very laborious. And I've always kind of been a lazy guy. And I'm like, there's got to be an easier way of doing this. So what I did one day is just for giggles. I knew we had a failure. We already figured out what chip it was. I put it back in there, fired the whole system up, right? And then immediately shut the thing down, pulled the circuit card out, right? My finger, and I started going across the chips. Got to the hot chip, and guess which chip was the hot chip? The failed component. So anyway, it was kind of funny. My colleagues thought like I was like into black magic and like voodoo, and because there'd be a problem with the chip, and then I'm like, okay, I'll figure out which one it is, but you're all going to have to leave, okay? And I actually started doing. I had a little mojo bag with some bones in it and a crow's foot, and I played the whole thing up, And we'd shut the thing down. I'd come out, U44. It's like, how the heck did you do that? I was looking at which chip was getting hot. The one that gets hot is the one that failed, and it's generating more heat, and that's what the problem is. So you could really determine, using a troubleshooting tool later on, if something's getting hot, and if you know what the norm is beyond that. Now they've got stuff on the market. They've got thermal imaging. Power voltage company actually uses thermal imaging. They'll go ahead with a thermal imaging gun and look at their power runs, and where two wires are joined together, if it starts to generate a lot of heat, they know there's a problem up there, okay? Because if it's generating heat, that shows that connection has too much resistance. Because resistance generates heat. So you can analyze, with thermal imaging, you can really see a picture of physically what's working and what's not working. So that's an advancement that's taken place really within the past decade. Thermal imaging now is pretty much mainstream. It's not that. Heck, you could get a non-contact infrared gun. You can get one at Harbor Freight Tools, for $19.95 with a laser. You pointed at it, and then that would have showed me exactly what me. I had to used to burn my fingertips finding the hot chip. Okay. Now you could just use one of those and say, oh yeah, this chip here is hotter than all the others that are doing the exact same job. This is where the failure is. Power is measured in watts. Watts is what power is measured in. It's not a question, it's a statement. Power is literally the product of current and voltage. Current times voltage. Any questions on power?
You were saying that to determine the total voltage drop across any component is a different formula than what it would be to calculate power. But in the book it says they both say P equals I times.
No. I'm just saying to determine how much power is being consumed across a component, you need to use that voltage drop across the component, not total voltage value. All right, let's go ahead and take a 13-minute break, and we're going to start up again at 6:35. 6:35.